Well, thank you for the kind introduction, Chris. So yeah, I'm going to try to get you to concurrent programs in Idris 2. It's at the back end of the talk. Hopefully we'll reach that part. So first we'll start with some motivation, which is just an excuse for me to draw some nice pictures. Then we'll see a little bit about Hoare logic and how we can use it to prove our programs, imperative programs, correct. And then how it fails us, ultimately. And the next evolution sort of being separation logic, which is more appropriate for concurrent programs. And finally, hopefully, we'll get to correct by construction programs. But first of all, I thought I should introduce myself so that if you want to have a chat later, if you're interested in any of these topics, so generic programming, proving, meta-programming and meta-proving or proof search, type-directed partial evaluation, staging, all sorts of things like that. Implementation of type theory, of course, and also interactive developer tooling. So I was really happy to see Xavier's talk this morning, like working really on that aspect. And the overarching theme of all of my research is just correctness by construction. So we want to write programs, and we don't want to be fixing bugs all day. All right, let's see if we can do that. So the first of all, the motivation for this work. Well, let's say we have an array of trees, and we want to apply the saw transformation on this array. And we have a small worker just turning a tree into a little bit of wood. And so that works, doing the next one, the next one, the next one, the next one. It's starting to be a bit heavy on the workload for this worker, so he's not too happy. And then eventually, I think he just gives up and is like, okay, there's got to be a better way. Like, I shouldn't have to chop down all of these trees. Maybe we shouldn't be chopping the trees, but we are.
Gives up, is there an error in the log?
No. Thank you. Thank you. So the goal is to then have a shared array of trees, and then we have multiple workers just going at it in parallel, or concurrently, I should say. So here we have 3 of them. They're also starting. They're in lockstep in that animation, but of course it doesn't need to be the case. And they're moving forward, etc. Ultimately, all of the trees that have been chopped down, we're really happy. Except that maybe we're not super careful when we implemented who was in charge of what part of the array. And some of them go a bit overboard. And they grab a chunk of wood that was already a tree that was cut down, and they refine it into a flute. So flute means shit in French. Right, so then we need a logic, basically, to avoid this kind of problems. We want to be able to say, okay, I wrote my programs, and actually, they will never go wrong like this. So the first attempt is Hoare logic. So Hoare logic is a logic for imperative programs. The general statements look something like this. And what's important to understand is that implicitly in all of the rules, there's a memory model. So the memory model is not made explicit, but when you're defining your rules, you're sort of implicitly introducing this memory model. Right? So what does this thing mean? Well, we're assuming that we can prove P about the world before we start. And then we run a command C. And after running C, we will guarantee that Q holds. Right? And you can see how this will be a good way to specify sort of stateful programs, right? If from the assumption, from no assumption at all, for instance, we can come to the conclusion that the array of trees has been completely cut down, then we know the program will be correct, and every single execution will just return the result that we want. Okay, so as I said, when we define such a logic, we start introducing some axioms that are describing the behavior of our programs, right? So the most basic one is the assignment axiom. So it's saying that assuming that L is a valid memory location, because you cannot just assign a memory location that doesn't actually exist. So here I don't actually care about the content of L, because I'm going to be overwriting it, right? That's the whole point of assignment. So I assign 0 to L, and then the conclusion from that is that L now points to 0. So it's just the meaning of the program, right? But we could also read it backwards, right? So what if I want L to point to 0? Well, if I've just assigned 0 to L, then the only precondition I need before calling my program is that L exists. And then what it contains doesn't actually matter. Right, so now we can prove our programs that are doing one assignment correct. That's fantastic. What if we want to do a bit more work? Well, we just introduced a new axiom for sequential composition. And we're saying, well, if P was true and executing, actually I have annotations, C1 takes us to Q. Now Q is true. And if from Q being true and running C2, we can get to R being true, then the composition of C1 and C2 will take us from P to R. And Q is still sort of implicitly there. It's in the derivation. But at the end of the day, for our program, we only care about the precondition. And then through execution, whatever we can conclude about the final state the program is in. So we don't mention Q anymore. So we can do our first slightly more interesting proof. So we have this classic program which swaps two values that are stored in memory without allocating a third value. So first of all, if we're going to talk about two values, they better be existing, right? So we're going to say, okay, well, assuming that L1 points to A and that L2 points to B, then we are running the assignment of XOR L1, L2 to L1. So L1 currently points to A, L2 points to B. So the XOR is going to compute to XOR AB. And now we've stored that value at location L1. And we can then do the next step. So again, L1 points to XOR AB, L2 points to B. We're computing XOR L1, L2. So that's XOR, XOR AB, B. That's horrible to say. And then we store it into memory location L2. And then if we've done a bit of digital logic and so on, we know that XOR AB, B is equal to A. So we can simplify that expression here. So now we have this intermediate step. And finally, we have a last allocation. We're saying L1 becomes XOR L1, L2. Well, L1 points to XOR AB, L2 points to A. So the new value for L1 is XOR of XOR ABA. And L2 is not changed because we are doing assignment on L1. And again, this is something we can recognize. This is just equal to B. And because of the rule for composing for sequential composition, we can just forget about all of the intermediate steps and know how our very simple program with only 3 assignments, we know that it starts from the precondition that L1 points to A and L2 points to B, and it comes to the conclusion that L1 points to B and L2 points to A. So we've proven that we've implemented swap with no allocation. All right, so that's then the first issue is with this sequential rule. So we're saying it's composition, it's sequential composition of programs, but in terms of proof, it's not actually very compositional. Because if you look at it, the same P that you use to characterize the world upon which both C1 and C2 act is precisely the one that gets piped as the precondition for C1. But maybe P also talks about variables that are only modified by C2. And now C1 has this extra noise in its context, talking about all of these variables that we do not care about. And then it's throughout the rule, right? The Q that you get after C1 then gets piped into the precondition for C2. But maybe this Q is talking about variables that C1 modifies, but C2 doesn't care about. So it's not very local reasoning. We're always talking about the entire worlds that we're going to be considering. So what we would like to have is a rule like this that would allow us to do some local reasoning. So P, starting from P and running C, we can get Q, and then just throw in an extra R. So if R is also true before, then R stays true after. And that would give us the ability to do local reasoning. So to lift a very small result, like swap on 2 values, and embed it in a context where we're talking about hundreds of values, for instance. So in a sense, we want to be able to say that R is independent from P and Q, and therefore it can just be passed along. The problem is that what we want is this lifting operation, but what we get is nonsense. So I've put on the top right here a reminder of what the rule is. So we start from our assignment axiom, so this should be always true, right? And here I've just decided that the original, like the initial value is 1. I've set it to 1. So then matching the pattern we have in the rule, I'm saying, okay, P is L points to 1, Q is L points to 0, and now I'm going to pick an R. Does anyone have a suggestion for a nasty R to pick?
L points to 1?
Yeah, exactly. If you pick R being L points to 1, now on the left-hand side, you have something that still makes sense. You have L points to 1. And on the right-hand side, suddenly you're saying that 0 is equal to 1. So you can just throw your computer in the trash. You're not going to be able to do any computations with that. So the problem is that we said that our intuition was that R was independent from P and Q, but it's not actually enforced by the mathematical conjunction, notion of conjunction. So the trick is going to, of course, be to change the meaning of ends. And that's what separation logic gives you. So let's have a look at separation logic. So the problem here was that R was talking about L, even though the other ones were already talking about L. So we're somehow picking a non-independent context along which to lift our results. So the solution, of course, is to make the predicates support aware, so that the R talking about L is now not a valid option anymore if P and Q are already talking about L. And then, so we'll make the predicate support aware, and then the notion of conjunction we're going to use will just not allow you to do to form claims about overlapping regions. So they will just be assumed to be nonsensical. So the purely logical predicates like M and M, M plus N equals 3. So M and M are purely logical variables, a bit like A and B in the proof for swap. Because they're not actually talking about any memory location whatsoever, the support here will be empty. So I'm representing the support as a finite region of memory, but whatever. The points to predicates, it mentions exactly one location, and so the support will also record the fact that we're talking about that one memory location, right? And then the big question is, how do we define conjunction? So taking two arbitrary P and Q, how do we define? So star is the name of the separating conjunction in separation logic. Well, it depends. So we have to build it manually. If we are considering predicates with non-overlapping supports, then we'll be in a good situation. So if this is P support, this is Q support, you can maybe convince yourselves that this is non-overlapping. The P and Q, well, P star Q, I should say, is not defined as P and Q, but it has an extended support, which is the union of both of them, which makes a lot of sense from the point of view of the intuition that the support is exactly the variables that are mentioned in the expressions, right? So we've recovered conjunction in the case where it's non-overlapping. If it's overlapping, however, so I've used the same support for P, but the support for Q is a bit bigger, and in particular in the top left here, it's going to be overlapping with here, and here it's going to be, on the bottom left, it's also going to be overlapping. Well, okay, this is P support, this is Q support. And then if we try to build the new support, there is a conflict here, right? We sort of don't know where these locations are supposed to be mentioned. Is it on the P side or is it on the Q side? Well, we say this is just not a valid statement, and as a consequence, P star Q is defined to be the absurd predicate. So we're saying this is totally illegal, it should never happen, all right? So then we come back to what we wanted to establish in the beginning, a rule to reason locally and then lift your results to a more global state. So if we can go from P to Q and R is true and non-overlapping with P, then R remains true and non-overlapping with Q, because the premise is telling us that C really only acts on P and Q. It doesn't care about everything that's outside of that domain. All right? So revisiting the source of all of our problems, if we have this assignment axiom, we are in the same situation, right? We have P equals L points to 1 and Q equals L points to 2. And then we pick R to be L points to 1. So now, again, we have this L points to 0 and L points to 1 on the right-hand side. But we don't actually quite have that because the star, the separating conjunction, is defined so that if the two predicates are conflicting, then the thing is equal to the absurd predicate, the predicate that has no proof whatsoever. And we also have the same pattern on the left-hand side. Even though both statements agree, they're again making an illegal claim because both sides of the separating conjunction are mentioning L. So now it turns out that both sides reduce to the absurd predicate, and that's perfectly fine because you assumed that anything was going as a premise, and then you come up with the conclusion that anything is going. So you've not broken the world. It was already broken when someone tried to use that rule. All right? So it's important to understand what the meaning of this modified points to is. We write it the same way, but it doesn't mean the same thing anymore. It used to be that L points to V, was saying that L is a memory location, and inside of it, there's a V stored. Now you're saying, I own L, and it points to V. So you know that no one else is actually allowed to talk about L or modify it, which is why you can safely update it yourself. So ownership is globally unique. It's transferable. So if you're calling a function, you can just pass ownership along. And it allows these destructive updates. And somewhat paradoxically or ironically, the fact that ownership is globally unique is precisely what enables you to do local reasoning. Because you know that any move you're making locally cannot happen in parallel somewhere else because people just don't have the right to modify that value. And yeah, so all of this is implicitly enforced by the rules of the logic. And what people who build this kind of logics typically do is that then they describe a formal memory model and they prove that all of the axioms that they've introduced are actually respectful of the memory model, right? So you're syntactically deriving your proof of correction, and then you have a soundness lemma saying, given this memory model, assuming I have a state that respects the initial condition, going through the operational semantics of my program in the middle, I will end up in a state that respects the conclusion. But we are not going to do any of these proofs or whatever. The only thing we're interested in is in stealing all of these ideas to do correct by construction programs, to build correct by construction programs. And why are we doing this? Well, because old school verification, I like to call it the WTF loop. So you write code, then you test it, or you try to formalize it, right? And then you find a bug. So you go back to writing code, then you go back to your formalization, find another bug, you go back to writing code, etc., until eventually maybe hopefully there are no bugs left. And what we like to do in correct by construction software development is that you write a specification. Okay, that's easier said than done, but in some cases you can actually write a specification. And then in the dialogue with the compiler, you're interactively building the program in a way that will always be specification respecting. So Xavier this morning was showing you tactics that allow you to case split on an input, and you get a list of all of the valid cases. That's a specification respecting step, right? Because you will be forced to handle all of the possible inputs. The same for the constructors. You cannot use a constructor that's L-typed. And so some of the steps introduce further goals. If you case split on something with 10 constructors, you have to handle 10 matches, right? And what you do is that you keep refining these goals until everything is just trivial. So you use a variable or whatever, an existing function. So in this talk, I actually managed to make it to the code. We're going to talk about Idris 2. So let me introduce Idris 2 a little bit because it's not the most well-known languages. So it's a functional language. It has lambdas, pure functions, inductive types. So here I've written the swap function. It uses a pattern matching lambda, variables. It just to give you a feel of the syntax, right? It's dependently typed, so Edwin likes to call it first-class types, meaning that types are just standard values. Just like you can write a computation to describe a program, you can also write an arbitrary computation to describe your type. So here, my favorite one, because I'm a compiler developer, is the file location. It has a string telling you what the source file is, and then a line number and a column number telling you what the file location is. But if you look at the definition before, it's exactly the same thing, right? It's just a top-level definition. Itself has a type, the type is type, and it has a body defining what the file location is.
Is there a case discipline?
No, this is just me, I think. I mean, okay, so here, implicitly, all of the lowercase variables are automatically introduced in using printx polymorphism. Apart from that, uppercase letters on the left-hand side are assumed to be constructors, I think. And so you might be a bit familiar with dependent types like in ACTA or Haskell, sort of. Here we have what we call quantitative type theory, meaning that it's resource aware. So that's why I have this weird 0 here in front of the type. So this is the identity function, and I could just write it like this, but it is actually equivalent to implicitly introducing the type at an erased modality. So meaning that during compilation, during compilation, I have the guarantee that this will go away. And this is not limited to types. If you have values that are purely for specification purposes, you can just mark it as 0, and you know it will be erased during compilation. And as a consequence, you also prevent it from pattern matching on it, right? I mean, you can't do everything you want, but as a consequence, you have strong guarantees about it being removed. It is strict, so there's explicit laziness annotations, and it's compiled to Chez scheme. So let's see. Yes, I can. So this was just originally as a way to quickly get the language off the ground, but it turns out that Chez scheme is a fantastic, purely functional sort of untyped backend. And so if you're already doing a ton of type checking, if you're targeting Haskell as your backend, for instance, like Agda does, you need to insert a lot of unsafe courses everywhere. And this can like prevent some optimizations from firing. We don't have this problem in Chez scheme. And we can turn off all of the checks because we know that we're the responsible adult in the room. And it's so good that it was originally used as sort of a way to get the language off the ground, but now it's still the main backend because it just works. And this allows Idris to be self-hosted, which means it's reasonably fast, which means all of the improvements that go in the language immediately are usable in it. Well, not quite immediately, but they're usable in the next version of the compiler, right? And when I say reasonably fast, the whole compiler and the standard libraries, which are admittedly fairly small, compile in like 5 minutes. Okay. So the core idea of this talk, it's good that we're finally reaching that, it's to define a domain-specific language that internalizes the ideas behind separation logic so that we can write our programs in a correct by construction manner. We don't want to be writing C-looking codes and then going into the Iris prover, for instance, and slowly proving that our code actually has a bug, and then we need to go fix it, etc. We want to get it right the first time. So the trick here is to abuse linearity. So I showed you the 0 resource, but there's also the 1 resource saying that the thing is linear to encode this idea of global uniqueness. So that's a problem with the current Idris language. We don't have uniqueness types, but hopefully we can add them at some point. For now, we have to encode it. And as I said before, the points to predicate is really the core idea, right? We don't want to be manipulating row pointers all the time because someone else might actually have a copy of them or whatever. We want to be manipulating ownership proofs. So that we know that we actually have the right to perform updates. And finally, the last thing, so 2 out of these 3 things are coming from quantitative type theory, so this is a great innovation, is to rely on erasure to get rid of all of the specification data. So the whole point of working with memory locations is that we don't have a pure value hanging around, right? It's somewhere in a cell, but if the specification data remains at runtime, then you're doing the job twice, right? You're computing both the value you're putting in the memory cell, but also carrying along the pure value. That's useless, so let's not do that. All right, so let's start with some code. So the ownership types, I'm changing it up a little bit. So I'm not pointing to a single memory cell anymore because that's not super expressive. Instead, I have a region of memory. And between the start and the end, I know that we have the value v's. So it's just a contiguous memory block, right? And why do I carry the start and the end? Well, because it's the slice that I own. Other people may own other slices outside of that region. Well, of that same region, but outside of that segment. And in Idris, you just define it as an inductive type, which is parametrized by a bunch of things. So it's parametrized by the region. It's not an array or anything so that people cannot mess with it. It has a start and an end, and it just has a list of bytes. This is the type of bytes in Idris. And I'm not showing you the implementation of this type because, first of all, there's no data in there. And second of all, I'm not showing my users the implementation because they don't have, the constructor is not exported. They don't have the right to manufacture their own ownership proofs. Otherwise, they could fake ownership and they could just do evil things. So the only way to get your hands on one of these is to use the primitives in the library that are all invariant respecting. Okay. So the first thing to do is to encode this idea that if you actually own a memory location, you can read from it. That's the most basic thing you can do. So let's say that you have an index, because remember now we're talking about slices of contiguous memory locations, and we want to get the byte at that index. The name of the region is sort of ambient. So for this to make sense, first of all, you should own the region. Otherwise, you don't get to read from it. And then the index should be in range for the part of the region you own. So you could say that this is between start and end, or here between 0 and the size of the list that describes the bytes that are in the region. And then from that, what do you get? Well, you still own the region because you only read from it. You didn't destroy it or anything. And then on top of that, you get the knowledge that the value v that you read is equal precisely to the value stored in the list at that index. Yep.
The v here is not taking part of the memory model, so it's supposed to be a local variable in the memory of the program.
Yep. Yeah, it's something it's a lead binding of sorts. Yeah, that's a good point. So how do you encode this in Idris? Ignore some of the noise, so linear I/O, whatever, it's because we're using linearity. I have my owned region between the start and the end. It contains v's. As you can see, I have not bound v's, therefore it's implicitly introduced at the beginning as an erased quantity, so it will not be there at runtime. Then I have an index, which is just an at, but I also have an erased proof that this index is within the bounds of these. So it actually makes sense as something to look up in these. And then the result of reading that byte is, again, this is part of the encoding. It's just saying this is some kind of I/O which returns a linear result, where I'm getting both, well, another proof that I own the region, because when I call that function, remember, my ownership proof was unique. It's getting consumed here. It's disappearing. So the function needs to return it, just like the separation logic sequence is like returning the proof in the result. And then I'm also returning singleton of index IDX V's. So this is looking up the value in the list. And singleton is a thing that's tying specification level values, which will be erased during compilation, to actual runtime values. So you can think of it as a box that contains a value which is known to be equal to the lookup inside of these. Of course, after compilation, it's not a box anymore and so on. It's all fine, don't worry, just a single byte at runtime. Okay, so we've seen read. Maybe we can move forward a bit on the write. So when do you get to write a value inside of the array? Well, first of all, you better be owning the region you're trying to write into. The index better be a valid one. And then what do you get at the end? You get another proof that you own the region, but now the content has been updated so that the new value is sitting inside the contiguous block of memory. And if you translate that into an Idris primitive, so again, you're setting the byte, you own the region, you're going to consume that proof, you have an index, it's a valid one, you have a byte that you want to write, and eventually what you get back is a new proof of ownership where the value has been put inside of the list. Right. Then we can do split. Okay. So this is more slice manipulation, right? So if you have an array and you want to split it into halves, you can. So this is saying that if I own a region that has this sort of shape, and I know that the first half has, well, half has this size, I can split at that size, and I will get two ownership proofs, one for the left bit and one for the right bit. And the code in Idris is saying exactly the same thing. These things are erased, I get the index, it's the size of these. If I own the region with V's and W's, I consume that proof, and I get a pair of two new ownership proofs corresponding to the two halves. All right. We can go the other way. If you have two contiguous blocks of memory, so you own a region between the start and the middle of the end, you can glue them back together and then just get a single ownership proof from the start to the end with the appended values in between. So the idea now is to write our map function using this primitive so that we can distribute the work, but in a way that's completely safe, in a way that's proven correct. And this is the type that we want to achieve. So it's saying, again, there's a bit of noise, but we have a saw from bytes to bytes. We have a region that contains trees, and eventually we'll consume it, and through some I/O process, we'll return a region that has the same endpoints and that contains the trees that have been sawn down. So first of all, we need to implement the sequential map. And to do that, we need to realize that there's we don't jump straight from having only trees to only having sown trees, right? There's an intermediate step, that corresponds to a loop invariant in a sense, right? Because we're really iterating over the array, one value at a time until we reach the end. And so we can encode that type like this. It's saying that no matter where the current split is between the trees on the left that have been sown already and the trees on the right that we still need to process, we'll eventually manage to, I don't have an animation for that, to go all the way to the end where we've sown both the left and the right. Don't look at the symbol, it doesn't matter. And once we have the sequential map, we can actually generically parallelize it. So the idea is fairly simple, right? It's the intuitive. You just split your region in two, you process it in parallel, and then you reconcile the two halves. So we can define this half function in terms of the primitives I showed earlier, splitting a region with a start and an end and some trees into something that has new boundaries, but that correspond to taking the first M trees and dropping the first M trees in the two halves. Then we have a combinator that allows us to evaluate something that produces an A, something that produces a B in parallel, and it gives us a pair of an A and a B. And so putting it all together, if we know how to do map already, but maybe not in a parallel manner, and we have a soul and a buffer, we can split the array of tree into a left one and a right one. In parallel, we can use the previous map to process the two halves. Then we combine them, and then there's a bit of like theorem proving to prove that map of take and drop, etc., is just the usual map. And you can do the same for reduce, using the rules of the monoid, etc., of monoids to prove that your parallel reduce is correct. All right, so what's next? Well, separation logic has a lot more to offer. There's a lot more we can steal from it to do our correct by construction programs. There's partial ownership. So you can split an ownership proof into tiny bits that you can then distribute to people. So they don't have the right to update the memory cell anymore, but they can read from it. And eventually they can return their share of the ownership so that someone can, again, reconstitute a full ownership, which entitles them to do an update. There's locks, which are relaxing the ownership from globally unique to globally unique at every point in time. So different people can access that resource just as long as it's always a single person at every point in time. And there's ghost states, there's more. And then on the more application sides, we can use these primitives to write all sorts of nice correct by construction programs that are reintroducing a lot of abstraction layers on top of just manipulating buffers of bytes, which is a bit low level. All right, I think that's me. So I'm happy to chat if you have any questions or even afterwards. And given that you're here, you might be interested in Types 2025. It's in Glasgow. You can come hike in the Scottish mountains yourselves. Yeah.
Thank you very much. You were perfectly in time. So we have now time for questions. Are there any questions? Yeah.
Hello. So as someone who's not as deep within these topics, what is the path from manually passing all of these regions and passing every single operation within the types path to having this form of ownership but implicit, so there's a lot of manual.
Well, I don't know about that. So, I mean, the idea here is really to start from your specification, right? Okay, so you start from your specification, you want to apply some kind of map, and then you have a library of functions that are telling you, just don't worry about this. This is the important bit. It's telling you, I'm starting from trees, and I'm giving you a map applied to them. So then, instead of composing folds and maps on pure values, you're just composing folds and maps, but over I/O processes that are doing all of the buffer and ownership management and so on. Right? So instead of having an input list, you have an input region, but you're not really talking about the regions that explicitly.
Yeah, I mean, it's in your words, you're like, ignore the noise.
Yeah.
On most of the slides. So there's just a lot going on to communicate this.
Yeah, when I look at this slide, the only thing I see is that.
But I guess, could you imagine a language like Rust, where these inferences get done in the background?
Right, but then what does it mean to do correct by construction in Rust, right? So you do the ownership transfer and so on, but you're not talking about the computation you're realizing anymore, in a sense. So that's my issue with it, right? So the idea for this is not to replace your Rust program, it's to replace your Rust program plus the iris proof that it's correct. So you would, in theory, you would have done the iris proof too, which is also needed. Yeah.
Implicitly, you are manipulating pointers here, but what happens if your map changes the size of the thing you're mapping?
So
there are different combinator or different.
Well, yeah. So I haven't done it yet because I'm trying to get some funding to do this work. But the idea is to reintroduce these levels of abstraction on top, so that you can do programming over serialized data, for instance. In which case the map might change the size, and then you will need to reallocate. So we have an allocate primitive, right? And allocation just gives you a proof of ownership with a random, well, not a random, an unspecified list of values because you don't know what's in whatever you've allocated. So you just know it exists. Yeah.
Yes, starting with this one.
Okay. Can you go back to the split example? I have a question.
This one?
Yes, in the top, at the top, the
Yeah.
second part of the concatenation, how would this BS equals M display in the framework representation?
I'm sorry.
I mean, it's not a location we're talking about in the second line. The BS equals M.
Here, the length
Yeah,
of, yeah, so it's a purely logical predicate. Yeah.
Yeah,
it's
those won't need any contradictions, right?
No, they don't have any support. Yeah.
Yeah, I'm just curious. I mean, you alluded to this. So, what actually happens at runtime when you run this thing? So, what's the runtime representation, and what actually happens?
Well, it depends what backend you pick. If
Okay.
you go with Scheme, I don't know how it works.
Okay.
But we have a shared reference to the same array or something. I don't know.
Okay.
But I mean, morally under the hood. Well, for the combine, for instance, that's tricky, right? So combine here, we have two pointers to the same array, right? And we return a single one. So it's arbitrary. I can't remember whether I return the left or the right one.
And let's imagine that I'm a low-level programmer. Are you suggesting that I should probably using something like Idris or Cosmos to write specification in order to be able to deal with file envelope, or to write the program in Idris to have a nice feedback and maybe a cool function test, or just to give up with the camera and start using Idris and language?
Idris used to have a malfunction backend,
Yes.
so that you could link against Camel, right? So that would be my suggestion. Please bring back the malfunction backend, and then you can write your program in Idris.
Thank you.
So one quick one, and then we need to stop. Yeah.
Okay. So you mentioned in the beginning you were using this quantitative aspect of Idris.
Yeah.
So how much do you rely on that? So you also mentioned that you said you wanted to have uniqueness types really. So
Yeah.
what's the role of that? Is that key to have linearity or uniqueness or what?
Right, so I use linearity to encode uniqueness. So linearity is a promise on the future, right? You're saying this will be used exactly once by me and the people I pass it to. Whereas uniqueness is a promise about the past. It's like no one has duplicated it. You can duplicate something that you own and then pass it as a linear reference to someone. So the way I do it in the library, I'm only providing you with a given set of primitives, and all of them are ensuring it's not just linear, it's unique. But this is implicit in the design of the library. Because if we had proper uniqueness types, we would be able to actually have it checked by the system and then be a bit safer on that front.
But it's a key thing. You couldn't do it without linearity or uniqueness.
Yeah, otherwise you can just duplicate your ownership proofs and anyone can do the updates and we're back to square one.